Hi everyone, today we will be solving Leetcode question number 851, loud and rich. Let's see what the problem statement is. So you are given a group of n people labeled from 0 to n minus 1, where each person has a different amount of money and different level of quietness. So in the input format, you are given a richer array and a quiet array. So the richer array is basically an array, you can say a vector of vector. So it has for every element I in richer array, it will have a vector of two elements in which AI and BI indicate that AI has more money than BI, right? And in the quiet array, there are n elements in which it denotes the quietness of every person, right? So now the goal is to return an integer array answer such that answer of x equals to y. So the question is, what is y here, right? So y is the least quiet person. That is, the y is the person with smallest value of quietness of y among all the people who definitely have equal or more money than person x, right? So let's understand what this actually means. Let's say suppose X has more money than Y, right? And Y has more money than Z. Okay. So this also means that X has more money than Y and X also has more money than Z. Right? So basically we can come to a conclusion that X has more money than Y and X has more money than Z, right? So we know that X has more money than both of them. So my answer of X will basically contain the minimum of the quietness value of both these Y and Z. So if the quietness value of Y is, let's say, 7 and quietness value of Z is, let's say, 5, right? So the answer, the quietness value of Z is less than quietness value of I. So answer of X will have Z in its value, right? So this is the format in which you have to return the answer. Now let's see the algorithm here. So we will be using DFS, and the reason that we are going to create a graph here is because we are kind of given relationships between people on the basis of the money they have, right? So that relationship diagram can be very well understood and coded if it is in the form of graph, right? So let's create the graph with what logic, right? So when you come to the first element, you have 1 and 0. So this means that 1 has more money than 0, right? So in such a case, we are going to construct an edge between 1 and 0. So I will be constructing a reverse edge just to for my convenience according to the algorithm. So so if I construct an edge such that, like this, from 0 to 1, this means that 1 has more money than 0, right? So I constructed a reverse edge. So in this case, 2 has more money than 1. So I'll construct an edge from 1 to 2. Then 3 has more money than 1, so I'll construct an edge from 1 to 3. Then 3 has more money than 7, so I'll construct an edge from 7 to 3, right? Then 4 has more money than 3, so I'll have to construct an edge from 3 to 4. Then 5 has more money than 3, so we will construct an edge from 3 to 5. Then 6 also has more money than 3, so we will construct an edge from 3 to 6. So we have completed our graph. So this is what the graph we have made, then it's a directed one, right? So now what to do with this graph? So we have constructed the relationship of the amount of money between each and every person. So you can see that this denotes 0 to 1 relationship denotes that 1 has more money than 0. And from 1 to 2 we see that 2 has more money than 1. So we also see that 2 has more money than 0 also, right? It's a basic transitive relation we have formed here. So this is what our logic is going to depend on. So we are going to construct an answer array in which all the elements are initially stored as -1, and this is an adjacency list because before making a graph, like while making a graph, so this graph is a pictorial representation, but in the code it will be stored in the form of an adjacency list, right? So let's create our adjacency list also from the pictorial representation that we had. So 0 has an edge to 1, then 1 has an edge to 2 and 3, and we have 3 over here. 3 has an edge to 4, 5 and 6. 5 and 6. So this doesn't have to be in sorted order. You can store it in any order. You can do it in the order which is specified in the question, right? So then we have 7 has an edge to 3, and that's it. We don't have an edge from 2, 6, 5 or 4, right? So we have our adjacency list done. So now let's see what to do after this. So after this, what we are going to do is, we are given n nodes. In this question, we have 8 nodes from 0 to 7, right? So we are going to loop, construct a for loop in which we are going to loop through all the nodes from 0 to 7. And then what we are going to do is, we are going to start the DFS. But we won't be doing DFS starting from every node, because we can do that, but if we do that, then the time complexity will be large enough to get accepted on Leetcode, and it is definitely not an efficient solution. So how are we going to make it efficient? We'll see that. So let's say that we start our DFS. So our first node is 0, right? From 0 to 7 when we are looping, our first node is 0. And let's create the indexes here. 0, 1, 2, 3, 4, 5, 6 and 7, right? So we started from 0 and we saw that answer of 0 is -1 right now. So this means that we have actually not stored the answer for the 0th node. So now let's start our DFS from here, and then we'll go to 1. Like we have an edge, 0 only has one edge to 1, right? So we'll reach 1. So the transitive relation that I mentioned you earlier was that if 0 has less money than 1 and 1 has less money than 2, then definitely 0 has less money than 2, right? So the concept that we are going to use over here to avoid using DFS calls at every node is that we are going to like traverse down to all its neighbors till we reach a node which has no further neighbors to go, right? So then we'll calculate the answer value for this node, and then we'll return it to the previous node. So when you return it to the previous node, then you see that like what is the minimum value. So in this case, suppose if we get the returned value from 2 as, say, 2 has a quietness value of 5, right? So 2 will return 5 to 1 and 1 has quietness value of 2, right? So we will have to take min of the returned value from this you can say this child node branch. So here it will be 5, and if there are more child node branches, so we have this child node branch also, and there can be many, 1 3 4, 1 3 6 and 1 3 5. So we have to, if we are on a particular node and we have different child branches below that, then we have to take the minimum of all the child node branches that we can have. So we will take the minimum of the path from 1 to 2, 1 3 6, 1 3 5 and 1 3 4, and also the value present at 1, because it can also have equal money, right? So that can be equal to its own quietness value. So we have to take the minimum of all these values, and that will be stored in our answer. So now let's try run it so that it becomes more understandable. So we were on 0, right? So we saw the adjacency list and then we moved to 1 because we have a neighbor 1. So we are now on 1, and from 1 we can go to 2 first. Let's go to 2 first. So when we come to 2, we see that 2 has no more children because 2 is the like a kind of a dead end, or maybe the leaf node you can say. So it's kind of a dead end. We don't have any other children below it. So this means that 2 is the bottommost point that we had to reach. So we will see the quietness value of 2. So the quietness value of 2 is 5 here, right? So for 2, there is no person which has a greater amount of money than 2 because we don't have any edge below it, right? So 2 does not have a person which has a greater amount of money. So we will have to store the quietness value of 2 itself in answer of 2. So in this case, in answer of 2, we will store 5. The quietness value of 2 was 5, right? So we stored 5. So now we are going to return that 5 value to here. So now 1 has that 5 value, receive that 5 value. So now we check that what is the current minimum. So the quietness value of 1 is 2 and the return value from this child branch is 5. So the minimum of 2 and 5 is, we can create a minimum. So minimum of 2 and 5 is currently 2, right? So now we have current minimum as 2. Now we go to one's next neighbor that we have. So we visited 2, now we can go to 3 also. So we went to 3 and then we saw that 3 has more neighbors to go. It's not a dead end, right? So we'll have to traverse more. So let's traverse to the first neighbor to 3, that is 4. So we come to 4 and see that 4 is the dead end. So the minimum value at 3 will be the currently will be the quietness value of 3, 0, 1, 2, 3, and that is 4, right? So currently it is 4 for 3. So we are on 3. Now when we go to 4, we see it's a dead end. So there can be no node which will have a greater which will be richer than this 4, right? Because we don't have any other child edge from there. So this means that in answer of 4, we have to store the quietness value of 4 only. The quietness value of 4 is 6. So in 4, let's make this 6. So this will be 6, right? So now we return the value 6 to this parent node from where we came. So now we have 4, which is the quietness value of 3, and we received 6. So what is minimum? So the minimum is still 4. So we'll keep the minimum as 4, right? Then we go to the next child, that is 5. Then we come to 5 and see that 5 is again a dead end. So we cannot have any other node which is richer than 5. So answer of 5 will contain the quietness value of 5 itself. So the quietness value of 5 is 1. So one thing that I did wrong here, we don't have to actually store the quietness values. We have to store the like, just a minute. Yeah, we have to store the node value, not the quietness value, right? So we stored 5, the node value of 5 was 2, and in this case we have 4. So every like dead end will contain the similar value because we cannot have any richer node, right? So in case of 5 also, we are going to store 5 over here. And similarly, if then we go back and we return the quietness value. So the quietness value of node 5 is 1. So now you see we have minimum as 4 and then we got 1 from its child, one of its child. So minimum value will be updated to 1, right? Then we go to 6, that is the next neighbor of 3, and 6 is again a dead end. So for dead ends we cannot have any richer node than that node. So we'll store the same node's value. and then we return the quietness value of 6. So the quietness value of 6 is 7. So 7 and 1. So from 1 and 7, the minimum value will remain 1 only, right? So now, once you have done traversing all the neighbors of 3, you have the answer of 3 as the minimum value, that is 1. So for 3, we are going to store 1 over here, right? So we computed a lot of values in just one DFS call, right? So that's great, because we don't have to start the DFS from 2 again and then 3 again to do the same recomputation. So this is what we can say kind of memoization that we are doing here, because we are like reducing the number of DFS calls that are unnecessary in this case, right? So in just one call, we have computed so many values. Let's see what more can we compute. So now we are on 3. We computed the answer of 3. And then you see that we came to 3 from 1. So we'll have to go back. And when you go back to 1, you see it will return, 3 will have to return its minimum value, right? So once 3 returns its minimum value, so its minimum value is 1, and the current minimum was 2, so it will get updated, right? So it will get updated, and then you see that it's like these values are the quietness values. So for 1, we have no other neighbor to travel, so we'll store the answer of 1. So in answer of 1, we'll store the node which has quietness value as minimum, that is 1. So the quietness value of 1 is for the node 5. So we are going to store node 5 here, and also I did the same mistake. We had not to store the quietness value, we had to store the node value. So we have to store the node value, it will be 5 over here. And then now we are done at 1, so we have no more neighbors, so we'll go back to 0, and then 0 had the current minimum value as its own quietness value, that was 3, but we received a lower quietness value, so it will be updated to 1. So the quietness value, like the node 5, you can see has the quietness value 1. So in 0 also we'll update the answer with 5, right? So you can see we are almost done filling all the array. Just one element is left, that is 7, in just one DFS call, right? So now let's go back to the for loop that we had created. So now you see that you called on 0, because initially it was -1, right? So you check all the elements in the traversal and see that if there is an element which we couldn't travel to store the answer in that previous DFS call. So in this case only 7 is left. So we will make a call to 7, because it is -1 currently. So we make a call to 7, and now we are on 7. So the minimum value currently will be the quietness value of 7, that is 0, right? So from 7 you can go to 3, and you go to 3, but you see that we have already computed the result for 3, right? So why do that computation again? You'll have to go through the go through the same paths from 3 to 4, 3 to 5, and 3 to 6 again. But we have already done that. We already know the answer for 3, so we don't have to again do it. So since it's pre-calculated, so you 3 will just say that I have already calculated my value, so I will just return you that value. So for 3, we stored 5 node, right? But the node 5's quietness value was 1. So 3 is going to return, we are going to always return the quietness value, not the node. So 3 is going to return 1. But the minimum value for node 7 was already 0, right? It's its own quietness value, so we don't have to update it. So we are done, because 7 had just one neighbor, and it will be 0. So 0 quietness value corresponds to the node 7. So we are going to write the value node 7 over here. So we are done with the answer. Let's check our answer once. The answer is 55254567. 55254567. That is what the answer we got, and this ends our answer, and we can return the answer. So due to this, avoiding the recomputations that we like thought of in our algorithm plays a very important role in reducing the time complexity, and the time complexity here will be O of n square in worst case. N square because there can be a case, right, where you have this kind of a graph, 0 to 1 and then 1 to 2, then 2 to 3. This means that you will have to travel to all the nodes once. Like it's like for 0, you have like almost all other elements which are richer than 0. So in that case, so it has to go up to n square if this is the case of graph. So the worst case will be O of n square, and the space complexity is also O of n square because we are constructing the adjacency list over here. So that's it. Now let's code the solution. So we are going to create an unordered map in which we are going to use it to create an adjacency list, right? So we created a map, and also we'll create a vector in answer that will be containing -1, and it will be of length n. So we also need to define n. So n is basically the quiet size. So we got our n, and the next step is to create an adjacency list. So for that we'll have to loop through the richer array, and then you need to create an adjacency list. By this, we were always constructing a reverse edge, right? So we are going to do it like this: dot pushback richer of I of 0. So we created our adjacency list successfully. Now the next step, as I told, is to go through all of the nodes from 0 to n minus 1 and see that do we need to make a DFS call or not. So we'll only have to make a DFS call if answer of I is equal to -1. That means that the answer has not been computed for that node. So we will have to make a DFS call. So we need to pass the adjacency list, the quiet vector, the answer vector, and of course the node. So and then in the end we are going to return answer, right? So now let's write the DFS function. So every time we are going to return the quietness value of the child branch, so the return type will be int, and let's create our function parameters. We need to ask quiet also, and then we need to pass our answer vector, and it has to be passed by reference because we want changes to be seen. And then we have a node, the current node, right? So the first step is basically, as we said, that for every node, it can definitely have a value equal to itself, right? Because as it said that it can have an equal money also. So in that case, we will create a variable x that will have that will basically store the current node we are on, and then we traverse Okay, we traverse through all the neighbors through the adjacency list of that node, and now see what we'll do. So if answer of I is not equals to 1, so this means that we have already pre-computed that answer, so we don't need to do it again. So we'll see what do we need to do in that case. If it has not been computed yet, so we need to compute it. So let's see how we'll compute it. In that case, let's create a variable in which I'm going to make a call, DFS call to its children. So in which I'll pass quiet, then answer, then the child, right? So I made a DFS call, and then once I receive, once I am going to receive the value of the, basically once we receive the value, so in this case what I am going to do is, then I am going to make a comparison that the quietness value between quietness value of x and quietness value of y. So yeah, just a small change. Instead of returning the quietness value, I'm returning the nodes because we have to store the node value, not the quietness value in the output, right? So once we have the node, right? So we are going to, this node basically will be the immediate neighbor of x that we had over here, and we are going to see that what is the value it is, like what is the comparison between the quietness value of that neighbor and my current node in which I am on. So if if the quietness value of the current node is greater than the quietness value that is being returned by its neighbor, then we need to do x equals to y, because now we need to update it with the node which is going to return the minimum quietness value, right? And we are done with this, and in the end we have to return answer of, like while returning you also need to store so that you do memoization. Answer of node is equal to x. So x will either be as of the same content as of node, and it can also update it to some other value depending on the lowest quietness value possible, right? So this was the case when answer of I is equal to -1. What if the answer has already been computed? So in that case, we are going to do the same check, but we don't have to make a DFS call again. So in that case, we'll see that if answer of I is less than the quiet value of x, in that case x will be made as answer of y. It's just the same thing that we did over here with y, but we don't have to make a DFS call because the answer is pre-computed, right? So then you're gonna store it. Okay, so one thing, that return statement has to go outside the for loop. Yeah, and then we are done. Let's try submitting it. Yeah, so we got accepted for this test case. Now let's submit for all test cases. Okay, so we got a wrong answer. Yeah, so the the reason why we got wrong answer was that the answer of I basically contains the node value, so we need to compare it with the quietness value. So I hope it will solve the problem now. Yeah, so you can see it has been accepted, and that was the coding part. Thank you for watching the video.